So in particular, I want to talk today about data processing pipelines with coroutines. So this is me. You can reach me in various places. I am currently still one of the co-organizers of the Munich C++ user group. Since the start of the pandemic, we've been doing online meetups. So feel free to join us there. We usually meet for once a month, and we have quite some interesting talks usually. In my day job, I currently work as a runtime engineer for Woven Planet, which is a company founded by Toyota that writes software for the automotive industry. So what do I mean by data processing pipelines? So the motivation came to me when in one of my personal projects, actually like in two different projects, I ran into two different problems that were quite similar. The one was I wanted to write an application that backs up files from the hard disk to the cloud. So I wanted to read a file from the disk, compress it, encrypt it, and then upload it to a server. The other problem was I wanted to read a file from a network stream, decode it, and then output it to an audio device, like media streaming of MP3 files, stuff like that. And as you can see already from the pictures, those two problems have quite a lot in common. It's always like having data flowing through these different processing steps. So what I wanted was to have a generic way that allowed me to implement arbitrary processing steps, have a unified way to compose these steps into a full pipeline, have detailed control about the control flows. So in particular, I wanted to be able to control when and how each step does executed, like when do I hand over to the next step, on which thread does each individual step execute, stuff like this. I also wanted to decouple these concerns as much as possible so that I could change them independently without having to touch the entire code base. So what I had in mind in the beginning was something like this, inspired by what we got with the ranges library in C++20, and then just be able to insert arbitrary steps there and switch stuff around. So what we're going to talk about today is I'm going to start by trying to derive a general interface for these different processing steps that compose our pipeline. Then we're going to look into how we can put these steps together to form like a full processing pipelines. Then we're going to look at like different control flows that we can use to execute this pipeline, which will lead us to coroutines. And this will be the second half of the talk then. I will try to give a brief introduction to coroutines, and then talk about how coroutines can help us model this control flow for executing such processing pipelines. So there's a lot of code examples on these slides. None of it is production quality. Lots of it has been shortened to fit on the slides. I'm going to omit lots of details, in particular also details about coroutines, because it's a very complex topic. So please try to follow the ideas, but don't try to use this code in production. I'm also going to go quite quickly about a few of the code examples, so don't try to follow every detail. It's really enough if you get the big picture. So the anatomy of a pipeline. We will have some source node that produces data by reading it from a disk, for example. We will have a sync node that will consume data, and in the middle we will have these filter steps that transform the data in some way, like compression, for example, or decoding. We can have also branches in pipelines that, like at one point, we branch into two different filters. I'm not going to show examples for this on the slide, but if you follow everything through that I do here, then extending this to allow branches in pipelines is actually quite straightforward. So the first thing that I wondered about is there a universal interface for these things? Like, can I give like a universal interface for a source or for a filter that will then fit all of the possible things that I would want to put in there? So The thing that I took for example, for inspiration here is I looked at like third-party libraries that perform tasks that could fit in such a step. And the first one that I stumbled across was this one. Maybe somebody recognizes it already. This is Zlib, which is quite a ubiquitous library. And it turns out that the interface that Zlib provides is pretty well suited already. Like if you can model Zlib well, then you can model pretty much everything that you would want to fit into such a filter. So the way that Zlib works is you have this ZStream object at the center. Then you specify an input buffer and an output buffer. And then you keep calling a pump. In this case, for compression, this is the deflate function. So the deflate function will run until either the input buffer or the output buffer is exhausted. So the sequence of events is like this. Before each call, you make sure that both an input buffer and an output buffer are set. Then you call the pump, like the deflate function. And this will keep running until one of the buffers is exhausted. Then you refill the buffer that has run out, and you just keep pumping until you've run through your entire input buffer. And at that point, you enter this finalization or flushing phase where you need to keep pumping until also all the output has been written that is still pending. And once that is also done, then you're through with the processing. So in C++, this could look like this. So simplest way to model this, I just have a struct filter which takes an input range, an output range, and then I have this single process function, which with each call it will tell me whether it wants to continue, whether it's done, or whether it encountered an error. I can also express this in terms of C++20 concepts. So the most general thing is a pipeline stage, which is just anything that has such a process function, which returns this process return value. Then a source is a pipeline stage that has an output buffer. And you may notice this little ampersand here that is the way in a concept to check for a member field. If you want to know why I added a link here, it's quite technical and rather boring, but we as C++ people sometimes like these details. So Async, the equivalent is a pipeline stage with an input buffer, and then a filter is simply the combination of both, something that has both an input and an output. So to make this a bit more concrete, let's just try to implement a source. In this case, like a simple file source. I just construct the file source, giving it a file name. It will open the file. And then with each call to the process function, it will fill the output buffer with the contents from the file. In the process function, I first check whether everything is set up correctly. The file needs to be open. I need to have an output buffer available that I can write to. If all of this is there, then I just read the pending data from the file. So I keep walking through the file by these successive calls. I then, after the reading, adjust my output range. So usually this sets the output range to 0, except for the very last call where I may have read less than my buffer size, and then this will be a partial resize. Then I do some error handling. First I check whether I finished reading the file. Then I do some error handling. And if neither of those happens, I just ask to be called again to keep pumping more data. The file sync is pretty similar, so I'm not going to show it because it's rather boring. But we can look at a filter. So the simplest filter that I could think of is just the identity filter. The identity filter does not do nothing because my input buffer and my output buffer could be of different size. So it's like a buffer resizing operation through a copy, but it's still rather straightforward what happens. So again, I have to check that I actually have any input available, otherwise there's nothing to do. If I don't have an output buffer available, I cannot continue. But then I simply check like how much can I copy, and then I just do a mem copy from the input to the output. Then again, as before, I adjust the sizes of the span so that my caller knows in what state I left things. And then I just ask to be called again. A filter that's a little bit more interesting is the deflate filter. This is now implemented through Zlib. I'm using this ZStream object that we saw in the beginning, which is at the center of Zlib. I'm going to, in the constructor, I'm just going to initialize the library. In the destructor, I'm going to shut it down. So this is not too interesting. And then in the process function, first of all, I want to check whether I am actually in the state where I'm still processing input, or whether I'm already in this final flush stage where I'm just pumping out output. I'm just checking the input, and if I have been called without an input buffer, then I'm going to assume that I'm in the flush stage. Otherwise, I'm going to set up the input buffer for Zlib. So I'm setting the appropriate fields on the ZStream. And then I'm also going to set up the output buffer. So I always need an output buffer. It does not really make sense to call process if you don't give it any place to write to. So here I'm going to complain if I don't find an output buffer. Otherwise, I again set up the respective fields. And as you may notice here, either of the two cases might happen, right? I don't know whether I need to, when I'm called with process, the previous call may have either run out of an input buffer or it may have run off an output buffer. So I need to treat both cases independently. And usually only one of the two happens. Then if I'm not in the flush stage, I'm simply going to pump. So I call deflate. It will run until one of the buffers is empty. I'm going to check how much input was consumed and how much output was consumed. And I'm going to set the ranges so that my caller can inspect which buffers it needs to provide me with before the next call. Then for the finalization stage where I flush, I call deflate with this zFinish parameter, which basically means like just keep pumping out output. There will be no more input. Then I keep doing this until I've gotten this zStream end return value, which signalizes that all of the data has been processed. In any case, I'm going to resize my output buffer. I don't have to do anything for the input. And if I reach the end, I'm going to reset the stream object and return to my caller that I've been done. And if I didn't hit any of the cases, then again, I'm just going to ask for more. I hope you see the pattern. It's always sort of the same. Always this process function just gets called in a loop until it's ran through all the data. So now I've implemented a bunch of these steps. They all have these very simple interfaces, just a single function and members for setting the buffers. Now the question is, how do I connect them into like a single pipeline where then the data sort of flows from one step to the next. So the first thing that I'm going to need is I need to take care of these buffers that sit in between the different steps. So what I'm going to use here is a simple ring buffer. Ring buffer that contains like a number of individual buffers which all have a certain size. And then it distinguishes between free buffers that are given out to the producers and the filled buffers which have been filled by the producers and are given out to the consumers. So this looks something like this, like I'm going to initialize a ring buffer. I say I want 4 buffers, and each buffer should be 1 kilobyte in size. And then it will get a data structure like this, and then a producer might ask to acquire a free buffer, which will then hand out the first buffer. It will get freed by the producer, returned to the queue. The producer might do the same thing for a second buffer. And then eventually the consumer will come in and consume the first filled buffer. So then the pointer on the right moves down. And this game then continues. So I can keep handing out free buffers and filled buffers. And then the consumer and the producer can both happily run on this queue. I might eventually reach a situation where I run out of either free buffers or filled buffers. So then I cannot, like if this happens, like in this case, I don't have any free buffers anymore. So of course, then I cannot hand out anything anymore. Pretty standard data structure. It's quite straightforward to implement. You basically need to keep track of the 2 pointers and then one counter, which helps you distinguish this case where everything is filled or everything is empty. So you need to count either the free cells or the filled cells to distinguish this case. So if you look closely at the interface from the beginning, then you might have noticed that my acquire functions hand out an object, which I called acquired buffer. The reason for this is that I need to distinguish basically between the point in time when the buffer was acquired and the point in time when whoever acquired this buffer finished using it. And this is why I'm going to use such a guard object for this. So it's a simple RAII guard, and I can release it either by letting it go out of scope, or in the case where I'm a producer, I usually want to tell the consumer downstream how many bytes of the buffer were actually written. That's why I have this commit bytes function. And this is how this is going to be used. So I just call one of the acquire buffer functions. It gives me back this guard object. I can call get buffer then to get an access to the span. And then I can write some data to it, for example, and then in the end I commit. So then when the consumer eventually acquires the filled buffer, it will then be able, it will then get the span of the correct size of the number of bytes that I've written into it. So putting this all together now, I arrange my steps in a pipeline, and between 2 steps I always insert such a buffer. The buffer on the left the step on the left will write into the buffer, and the step to the right of the buffer will consume the data from it. And the central role of the buffer here is really that any communication from one stage to the next flows through the buffer. That is really the key. As we've seen before, each step not only produces data, but also produces a return value. I'm not going to hand the return values directly from one step to the next, but instead I'm going to hand them through the buffer. So I'm going to define this, I called it operation state, which I'm then going to add on the buffer. So this is how I communicate to my neighboring stages. And as you can see, the operation states distinguish a little bit more than just the process states. In particular, I need to point out whether I'm in the finalized state, so that the node can determine whether it needs to expect additional inputs from its upstream buffer. So what do we have so far? We have the individual processing steps, source, sync, and filter. And we have these buffers that glue them together in the middle. So now let's actually try to execute some code on this. So the first thing that you might want to do is like just a very simple synchronous execution. So in this case, we actually only ever need a single buffer because we're going to execute all the steps one after another. So the source starts by writing into the buffer. Then it calls its downstream filter. The filter takes the input, transforms it into the output, then in turn calls the sync. The sync consumes the output, and then the whole thing starts again. I arranged the steps here in kind of a staircase pattern. And what that is supposed to hint at is that like all of these steps will be on the call stack, right? It's really like I start at the source then calls the filter, and the filter calls the sync. And they will all be on the call stack while this is executing. And then once the sync is done, the call stack will unwind, and then the source starts by pumping through the next buffer. So if I'm going to implement this, I will write an execute step function for each of the different stages. I'll start by the source. So you may notice these are actually now template functions using the concepts that we defined in the beginning. I'm using the shorthand syntax now. So basically in this case, source is a template parameter, and it can be instantiated with any type that fulfills the pipeline source concept from the beginning, right? So everything that has a process function and that has an output buffer is fine to use here. So I will need a loop. In the loop, I'm first going to acquire a free buffer from the ring buffer that I specified here. Then I'm going to hook up the buffer to the step, the processing step. Then I'm going to call the pump function, the process function. If that one is already finished, then I'm going to break out of the loop. Otherwise, I'm going to look at how many bytes have been written through the processing, going to commit the number of bytes so that my downstream can consume them. And then I actually have down here the function call to the downstream. So that is the mysterious third parameter here. So the way that this works is it's this call chain that we mentioned before, right? So the source calls its downstream step, which then goes through the same hoops, calls the downstream again. So I have all the functions on the call stack in the end. Let's look at the other end of it, the sync. So this is pretty much the polar opposite. The sync only gets an input buffer that has already been filled, sets it up to the processing step, calls the process function, and if it's done, it just returns. One thing that you may notice already, the source had a loop. The sync does not have a loop, right? Because the sync is only ever being called passively. So the whole execution is driven from the source in this case. So if I'm going to hook this up now on the user side, what I do is I first do the execute step of the source, and then I pass as this downstream object from the slide before the callback that then invokes the execute step function for the sync. So the only thing that's missing is the filter. So this filter should just be a combination of source and sink, right? Unfortunately, it's a bit more complicated than you might like it to be. The problem here is that processing the filter may either empty the in buffer or the out buffer, but not necessarily both. So if the output buffer is not filled, I need to return back to my producer to ask for additional input. But at the same time, I need to hold on to the RAII object for my output buffer, because I cannot commit that yet because it hasn't finished filling up. So our nice little design with the RAII object starts breaking down. And this can be solved, but it's not straightforward, and I'm not going to show any code for this. You're happy to try this out yourself. But this is already where you see that this problem of control flow can be surprisingly difficult, and it gets difficult very quickly. The other thing that is not nice here is, as we said before, the loop in this case is only in the source. So the source is pumping the whole pipeline. I can also do it the other way around and have the sink pump the pipeline so that like the sink keeps pulling from upstream the data. So like the sink calls the step doesn't have any input yet, so it calls the source, and then the whole thing flows through the pipeline the same way. The thing is, if I want to change from one approach to the other, I pretty much need to touch every bit of code that I've written except for the implementation of the steps themselves. So this is a pretty invasive change. And that's actually pretty weird, like that such a small change, because the two cases are completely symmetrical, has such a deep impact. So I'm not too happy with this. It works, but like the code that falls out of this, I don't like it. So let's try to do something else. So in the end, I probably want to execute some of these steps in parallel, right? I mean, there's one of the benefits of breaking computation down this way, that you can execute the independent steps in parallel and thereby speed up your performance. So what I'm going to do now is just have each of the steps run on its own thread. And now the ring buffers in between, of course, they can be accessed concurrently, so they need to be synchronized. Fortunately, this is just a single producer, single consumer scenario. I'm going to do the most straightforward thing here, just wrap the ring buffer into a thread-safe ring buffer, so empty ring buffer here for multi-threaded ring buffer. Really straightforward wrapping, just use a mutex to protect access to the data. And then I use a condition variable to wait for a buffer to become available if the buffer is already empty. So the way that this will work is if I don't have a buffer available, the condition variable will just go to sleep. And then the empty acquired buffer, which I return here, again, this is an RAII object, so whenever this gets destroyed, it will take care of notifying the other side, right? So if I acquired a free buffer, it will notify this wait for the filled buffer and vice versa, right? So that they can unblock each other. So this is not too exciting. So let's now look at how the execute step function implementation changes. So again, we start with the source. We have a loop again, so we keep looping while the process step wants to be fed more data. I'm going to acquire the output buffer that the source is going to write into. Then I just call the process function. If that one does not want to continue, I'm going to break out of the loop. Otherwise, I'm going to commit the data that was written into the out buffer. So there's no call now to the downstream function anymore, because each step runs in its own thread. They're running all the time, and they're just waiting on their buffer to receive data from their neighbors. So for example, if we look at the sync, same thing, a loop as long as it wants to keep going. And now the sync waits, calls acquire filled buffer. And in the beginning, that will probably block going into the wait on the condition variable, because there is no data that has been produced yet. Then once the source has ran through and committed something to the buffer, then this acquire filled buffer will return, and then I can continue. I set up the input for my processing step, call the process function, and if everything went well, I just keep going. Otherwise, I break out of the loop. And now, this time, I'm actually going to show the filter case. Still more complicated than the others, but it also starts with a loop. So the basic idea should be clear. I need to set up the input, I need to set up the output, and I need to call the process function. The first thing that I want to do is, because the output or the input may need to be retained through multiple iterations of the loop, I'm going to store the guard in an optional object. And this is how you get a nested type out of an argument that has been specified with concepts. I haven't found a shorter way to do this, unfortunately. I tried using decal type, but that didn't compile for some reason. In any case, if my input buffer is empty, then that means my optional is not holding on to any object at the moment, so I'm going to acquire one from the ring buffer, then set it up on the process step, then call the process function, and if that exhausted the input buffer, I'm going to release the RAII guard, thereby unblocking my neighbors from using this buffer again. For the output, it's pretty much the same thing. Again, acquire it from the respective queue, set up the process function. This time the releasing, I need to remember to actually tell how many bytes I've written of the output buffer, so I need this additional commit call, but otherwise it's pretty much symmetrical. And this is what it now looks like from the outside. So I put each execute step function in its own thread. They're all running concurrently. Of course, they're blocking a lot because they're waiting for buffers from their neighbors. But in theory, this is a design that actually works quite well. It's rather performant, and as long as I don't have too much stuff to execute, this is actually perfectly fine on a modern desktop machine to run this. It's very symmetrical. The code is quite straightforward. So yeah, this is not bad actually. So we've seen these three control flows now basically. So the two synchronous ones, the one that was producer driven, the other that was consumer driven, and then the threaded design. Where each step was basically running on its own, so they're all more or less equal. The interesting question is now, can I get such a symmetric control flow without having to spawn threads? So can I have a single threaded scenario that exhibits a similar control flow to what we had in the threaded case? And this is where the coroutines now enter the picture. So you can think of a coroutine, one way to think of a coroutine is like a function that can just be paused in the middle, right? So at any point, you can just suspend it. You can then pass the function object around, store it somewhere, and then at some later point, somebody's going to resume it, and it's going to continue execution right where it left off before. In C++, we only have stackless coroutines. That means when I'm going to suspend, control flow is always returned to my immediate caller. So I cannot resume like deep down in the call stack and then like resume like a whole stack of functions in between. As a user, I can recognize a coroutine. So if I want to tell whether a function is a coroutine, I basically need to look for these 3 keywords. If either of them appears in the function body, then it's a coroutine. We are mostly going to talk about the co-await tier, which is probably the most interesting of the 3 because that is what allows you to suspend a function. The co-return is really only interesting when the coroutine shuts down, and the co-yield is pretty much a special case of the co-await. So if you've understood the co-await, then the co-yield is not going to give you much trouble, probably. So the typical use cases that people look at when talking about coroutines is asynchronous computation is the one. So if you think about like you have a read function, for example, in a networking library that wants to read some data from a socket. The easiest way is to just use a blocking read, but of course that you might not want to do this for performance reasons. If you use an asynchronous read, for example, like Boost ASIO has been providing from the beginning, like the basic async read works like this, that you set up the read and then you give a callback as a parameter, and whenever the read finishes, your callback gets invoked. And what you see now here, if you compare the 2 calls, is you get this this weird inversion of control flow where I got the return values before, the EC and the bytes read, they now moved into the parameter list of the callback function. And if you're not used to writing code like this, this can be a bit difficult in the beginning. It's not impossibly hard, but it takes some getting used to. And it's a special way to think about code. And if you don't do this a lot, then you might have some trouble with this. What coroutines allow you to do is to flip the control flow back around. So with coroutines, instead, when you call the async read function, you would prefix it with the co-await, and now the results of the read are again just return values. So all of the code that comes below looks exactly like it looks in the blocking case. This is still an asynchronous execution, right? So at the moment that the async read returns, you're probably going to wake up on a different thread than where the async read call started, right? Because you're now being called back from whatever is driving the underlying I/O. So it doesn't execute in the same way as the one above, but in many cases, you don't need to think about this. You can just ignore this because depending on what you do after the read, it's very likely that none of this is affected by the fact that you went to sleep and then got awakened with from another parent or on another thread. The other use case that gets mentioned a lot with coroutines is this suspend resume. So examples for this are, for example, generator functions. So the idea here is that you start a computation, you get back a coroutine, and then you keep invoking the computation, potentially also providing it additional data with each invocation. and every time that you invoke it, you get a new result back, right? And so you can, like for a generator, for example, you can then loop over all the data that you get back. With each iteration of the loop, you get a new value back, and you just keep looping until the coroutine is done, or you don't want to continue anymore. So this is the suspend resume patterns, and this is really, like, from a user's point of view, usually when you're asking for coroutines, you want to do one of the two. Unfortunately, in the way that C++20 specified coroutines, you cannot just get one of the two. So the coroutines, how they're, what we have in the standard right now, it's pretty low-level feature. So you can implement both of these cases yourself, it's no problem, but you have to write a lot of code yourself, and you have to dive pretty deep into the feature. And it's a somewhat unique feature because it works differently from pretty much all the other language features that we have in the language at the moment, in a way. Because it sort of provides direct hooks into the compiler that allow you to insert code into, like, specific stages of this coroutine execution. And we're going to look at some concrete examples of how this works later on. So one of the big difficulties about the coroutine mechanisms is that there's a lot of moving parts that you need to keep in mind at the same time. And in the beginning, it's really not straightforward how they interact. I'm trying to give a quick overview here, but if you're hopelessly confused, like, don't be afraid to ask questions. And if you still don't get it, then this is normal, right? Like this takes some time getting used to. So, but I hope I can at least give a rough idea. So I think the three essential things that we need to look at is the return object of the coroutine function, the thing that is called the promise. This is a coroutine promise. This is not the STD promise from the STD future from the standard library, so please don't be confused by the name. And then what is called the awaitable. And we will look at each of those three in detail now. So the return object, this is literally the object that is being returned to the caller upon the initial call to the coroutine function. So if we take the suspend resume example from before again, the main function is going to call our coroutine, start computation, and then it's going to get back such a coroutine object. And this is necessary because the function may be suspended at some point in execution, and then, like, this suspended state of the function lives somewhere, right? So it needs to be represented in some form to the caller so that it can then later resume this execution, or, like, store it somewhere or whatever, right? But I need to return something that represents the state of the function in case that it goes into suspension. So how this is typically used is that upon construction of the coroutine object, which happens inside the coroutine, the caller doesn't do that himself, the object is passed in the constructor the coroutine handle. And the coroutine handle, that is like the pointer to this suspended function state. And it's really like a pointer. It's like a raw pointer. This thing does not have ownership. It is just like a handle through which I can reach the suspended state. The one important role that the coroutine object type has for the compiler is that it points out the promise through a nested promise type def. So these three objects that we had before, right, the return object, the awaitable, and the promise, these are three distinct types, right? So I somehow have to link them together. And this is how the compiler figures out, like when it sees the signature of a coroutine, looks at the return object, looks for a nested promise type def. If it cannot find one, then you will probably get a compile error. Otherwise, that is what your promise is going to be. So this is how it figures it out. This is already a little bit weird, like probably haven't seen this in any other feature, but this is how things are done in coroutines. Which brings us to the promise. So the promise is sort of a central point of interaction. In particular, it's the main point from within the coroutine to interact with its callers. It's constructed by the compiler at the start of the coroutine. This happens automatically, right? It looks for this promise type def, and then it sort of behind the scene silently constructs this promise. The promise also receives the initial function arguments that were passed to the coroutine call as arguments. The main role of the promise is that it determines what happens at essential points during the coroutine's lifetime. In particular, the start and the completion of the execution, right? So when I invoke the coroutine for the first time, or when the coroutine finishes execution, either by co-returning or by the control flow falling off the end. This is all where the promise has the opportunity to influence the behavior. The promise is also responsible for constructing the return object that gets returned to the caller. Right? So this is also a little bit confusing, because when you see the signature, then you think, okay, it's clear like the return object, that is like the return value, but you're not getting to the return in the call, right? Like you're probably hitting a suspend on the call, so you won't get to a return until much later. So the way that it works is the promise is actually the one, it has a special function called getReturnObject, which is again invoked behind the scenes by the compiler. That one constructs the return object, which is then stored away in a secret place. And then when I first resume again to my caller, I pass this out as a return value. This is a bit weird, but you just have to accept it because that's how this works. The promise also provides access to the coroutine handle. It has a function from promise that allows you to, if you have a promise in hand, to retrieve the respective handle, and you can also go the other way around. So this is actually quite nice. If you either have a coroutine handle in hand or a promise in hand, you can always go from one to the next. This makes it a bit easier figuring out how to access data, as we will see soon. Then the last object that we need to take a look at is the awaitable. So the awaitable is basically anything that I call co-await on. That's the simplest way, I think, to think about this. So in this case here, like we had this async read function. Before we just had this on a single line. We just called co-await async read. But what really happens behind the scene here is the async read object returns an awaitable, and then the operator co-await works on this awaitable. So it's a type that can be awaited on. That's why it's called awaitable. And what that does is the awaitable provides us the hooks to influence the behavior, what happens when I suspend a coroutine and when I resume a coroutine. That's its role. For instance, it might also decide not to suspend at all, like a co-await call also can return right away without giving up control flow. And the awaitable also gets past a handle to the running coroutine before suspension, and we will see in an example shortly why that is useful. So let's try writing the minimum possible code that uses coroutines. I'll let you stare at this for a second. So F1 has a co-return statement that makes it a coroutine. That means its return value has to be a coroutine object. So it needs to have this nested promise type. It needs to point this out, otherwise the compiler complains. For the caller, things look actually pretty straightforward. It just calls F1 and gets back the return object. So this promise type, we need to fill with live as well. We need to provide these functions. So the getReturnObject function, which we mentioned before, this is the place where the return object gets constructed. Then we have these two functions, initial suspend, final suspend. Initial suspend basically determines what happens at the start of the coroutine. Final suspend determines what happens at the exit of the coroutine. The simplest way to implement this is by returning one of those special awaitables, suspend never or suspend always. So in this case, when the coroutines start, we're not going to suspend, it's going to start executing right away. But when control flow falls off the end, like by reaching the co-return, then I'm actually going to suspend. In this case, execution is going to be stopped and control flow is passed to the caller. Then I also need to specify what happens with the final return value and if I encounter an unhandled exception. But this is pretty much the basics of what the promise does, right? So everything surrounding suspend and resume, I have some function to influence that here. So what happens now is that the compiler does a bunch of stuff behind the scenes. I try to sketch this out here. So whenever the coroutine is invoked, it first looks at the return type, determines the promise type from it. Then it's going to construct a promise. The constructor arguments to the promise are the same as the arguments that were passed to the function initially. Then I'm going to call getReturnObject and store this, whatever return object is returned there, away to pass to the caller later. And then the compiler is going to call co-await on this initial suspend. And what the co-await really does, we will see in a second. Then the function is going to execute. Eventually, it's going to return. And then at the point of the return, I'm again going to invoke the promise to handle the return value. In this case, we're going to return void, but it could also be like a proper return value. I'm going to co-await the final suspend, and then I'm going to destroy the promise here. Okay, so now let's actually take a look at suspension. So suspension happens whenever I await something, right? So this is why the awaitable comes into play here. So if I have a coroutine which calls co-await, then the awaitable needs to tell me three things. First of all, whether I need to suspend at all or whether I can just continue executing. This is what the await ready function does. In this case, I'm going to return false, which means I'm not ready. Please, I want to suspend execution, return control flow to my caller. If that happens, then await suspend is going to be invoked. So I can perform whatever things I want to perform before going to sleep. And then I go to sleep, control flow goes back to my caller, and my caller may eventually wake me up again. In that case, await resume gets called. I may do whatever things I want to do before waking up, and then execution continues where it left off. Now we've basically seen all of the parts. I haven't shown you everything about coroutines, but I've shown you everything that we need to follow the rest of the talk. This was a lot. It probably seems like lots of random stuff that is just floating around. I'm going to try to build some connections now that make it a little bit more clear how the things interact. So at the moment, I just have these things floating around, right? So I have the callee, which has this awaitable object that it constructs and then calls co-await on, right? So those two are obviously, like, they know each other, right? The callee, like, he's the one constructing the awaitable, so yeah, he has access to that one. The caller, which is not a coroutine, that's just a normal function. The callee is the coroutine. The caller gets the return object back from the initial call that constructs the coroutine, right? So it holds on to the return object. And then we have this promise and coroutine handle flying around somewhere. We've already seen that as soon as I have one of the two, I can just convert it into the other, but it's not really clear how they are connected to the rest. So let's make some acquaintances. So I already mentioned what you typically do when constructing the coroutine return object is you pass it the coroutine handle as a constructor parameter, and it can then just store it. You don't have to do this, but we're going to do this here because it's really a really useful thing to do. And somebody needs to store the handle, and usually the coroutine return object is a good place to hold on to this. So why does this work? Well, because the coroutine return object, if you remember, is being constructed by the promise. And if I have the promise, I also have the handle, right? Because I can go from the handle to the promise and vice versa. So because of this, the promise is responsible for constructing the object, so it's no problem for it to pass the handle as a constructor parameter. The return object can store it, and then the return object has a handle. Wonderful. Yes, please. Yes, exactly. Yes. So it's magically constructed by the compiler in some place, and usually it's on the heap. Yes. And the handle, exactly. The handle is a raw pointer to like all of the state associated with the coroutine. This includes the promise. This includes any local variables that might get suspended, and yeah, everything else. Exactly. Yeah. Any other questions at this point? Feel free to ask questions. We're doing quite well on time, I think. So this makes a connection here, right? Now I can get from the caller to the return object, and the return object has the handle. From the handle I can get the promise. So this side already now is not as isolated anymore. The question is what's with the callee? So the callee currently only has the awaitable. So we saw this before. The awaitable, when I call await suspend and I actually want to go to sleep, it's going to call this await suspend function. And the await suspend function gets passed. Again, this is done behind the scenes by the compiler. This gets passed a handle to the coroutine that is just going to sleep, right? So the coroutine calls co-await on the awaitable, and then basically passes a handle to itself as an argument to this await suspend function. And this now gives us a connection here, because now we can get from the awaitable to the coroutine handle, and now the whole thing fits together. And this is going to be our, still incomplete, there's still more, but this is all that we're going to talk about today. This is going to be our map, which we're going to use to navigate through coroutine land. So the two things that I really need to know how to do is, how can I pass data from the caller into the coroutine, and how can I pass data from the coroutine out to the caller? Let's start by passing the data out of the coroutine back to the caller. So I'm starting in the coroutine, in the callee somewhere. The only thing that I can reach is the awaitable, right? So let's look at the awaitable. What can I do here? So let's say I want to pass the integer 42 back to my caller. In the beginning, I only have access to the awaitable. So the 42 goes to the constructor parameter for the awaitable, right? This is just a normal object construction. The answer, curly 42, normal object construction, right? Just goes straight to the constructor. The constructor stores the data away. It now lives in the awaitable object. From the awaitable, the await suspend is my route to the coroutine handle, right? Because the await suspend, when it's invoked, gets past the coroutine handle as a parameter. Now I can use the value that I stored before in the constructor of the answer, and I pass that on to the promise. Okay, so the promise, this other object that lives in a completely different place. I build some storage there where I put my value, and then in the await suspend call, I can reach it, I can put the values there, and now my data lives in the promise. Okay, I've passed it down from the callee through this pass to the promise. And now I can reach the promise through this other path to get the thing back again. So I got back the return object, C1, and now the return object, that is my entry point to get to the promise. So I asked the return object, please give me the answer. And then implementing the get answer is pretty straightforward because remember we stored the handle before in the constructor of the return object, right? So the return object already has the handle as a member. And now the only thing that we do is in the get answer implementation, we go from the handle to the promise, and the promise has a field where we stored the data, right? The data already lives in promise, we just read it out, we give it back. This is the path out. Okay? You don't have to remember all this, but I hope you can follow how the argument goes here, right? You need to know what are the connections that bring me from one object to the next, and then you need to draw a map like we did before, and then like whenever you want to do something, you have to look at the map and think like, what gets me from here to there? And once you've figured this out, then you can work with coroutines. So let's do the other side. How can I get data from the outside into a coroutine? So the key is still to get to the promise, right? Because that's the only object that both sides can reach. And the path is the same as before. I have to go through the return object. So now instead of a getter, I add a setter function. I called it here provide to the coroutine object. And then eventually on the inside the coroutine, I want this value to resurface as the return value of the co-await call, right? So the control flow here is F1 starts executing, it gets until the co-await, then it suspends. F1 goes to sleep. Main now gets the execution, so it gets the return value C1. Main continues execution, it calls C1 provide. At this moment, the coroutine resumes, co-await returns, and the 42 that I passed to the provide is returned to the coroutine F1. It now has the value 42 stored in the answer, and it can continue executing, right? So the provide function does the exact opposite of what the getter function on the coroutine object did before in the other case. It has the handle as a member, goes from the handle to the promise. The promise has a field where we store the data. We just write it into there. The only thing that we now do in addition, we also resume the coroutine to execute. This doesn't have to be done in this way. We could also just resume it later, only store the data here. But since it's a small slide example, we're just going to resume it right away, right? And again, like, because the return object has access to the handle, it's able to do all of this. That's the connection here. So now again, we stored the data in the promise. The data now lives in the promise. And if we want to retrieve it from the other side, we have to go through the awaitable. Now, this path is not quite what is here on the map, as we will see. Because to get from the awaitable to the handle, this we relied on the argument to the await suspend, right? But at the moment when we want to retrieve the data from the outside, await suspend has already finished executing, right? Because await suspend is executed before we go to sleep. But now we're going to wake up, and when we're waking up, what is being called is await resume. And await resume does not have the handle anymore. So what we do is we remember the handle, right? So when await suspend is getting called, we store the handle inside the object, just in a member. And now when await resume gets called, then we remember the handle from before. When we wake up, we go from the handle to the promise. The promise has the value. And now the return value of the await resume, that is going to be the value that the coroutine receives when the co-await returns. So this is the path back. And these are really the essentials. Like this is the hello world that you need. And once you know how to do this, you basically know everything that you need to do. And anything else that the coroutines do is just a variation of this. So if you want to use coroutines, like keep thinking about this, keep practicing this until it starts to make sense. And eventually you will know where the parts belong, and then you can start working. So let's get back to work. Let's actually talk about pipelines again. So to use pipelines with coroutines, what I'm going to do is remember we wrote this implementation that was using the threads, right? Where each step was executed in its own loop on its own thread. We're going to use that as the basis, right? So we're going to grab these execute functions where each step is executing in its own loop, except that where in the threading case, these acquire functions were just blocking and waiting for the neighboring threads to do their work. We're now going to do a co-wait in these places, right? So if you think of coroutines as a form of cooperative multi-threading, then this makes perfect sense, right? Because like the acquire functions, that is the point where I give the other thread the opportunity to do something, right? That's where I say I'm waiting for you to fill a buffer for me, or to like remove a buffer from the queue and give me back the empty space. So this is the natural point where in a single-threaded scenario with coroutines, where I would say, like, here I want to relinquish control, and now somebody else gets the chance to execute something, and then maybe once they provided me with some input, then I want to wake up again and continue execution. So the crucial question now is actually, when I reach this co-await and I go to sleep, who do I pass control flow to? And the easiest answer there is that there is like some big scheduler running underneath, right? So all of these coroutines, I spin them up, I all hand them over to a scheduler. The scheduler then resumes the individual steps, and as soon as a step goes to sleep, it observes the state of all the steps, it observes the state of the queues in between, and then determines who to wake up, right? And the scheduler can make pretty sophisticated analysis here, like it can, for example, it might have information that like certain steps have a higher priority, certain steps are like more time critical than others, whatever, right? I mean, you can go arbitrarily crazy there. Like it's a scheduler, right? Go nuts. Another thing that I could do, instead of going to a scheduler, I could just go to a neighboring step. And this is something that that you also see quite often. So like, for example, the producer would call the consumer, and then whenever the consumer runs out of input, it would go into a co-await that would then suspend it and then hand control back to its producer, so that the producer has a chance to provide additional inputs, right? So it's like normal calls on the way down, right? And this is still, that's why it's still like steps down, because like the blue one, when the blue one is executing, the red one and the yellow one will still be on the call stack, right? What I added now is the ability to say, like in the middle of execution, okay, now please go one step up the call stack, and then this upstream step can provide additional input and then resume me right where I went off, right? So I no longer have these weird problems that I have to return at some point, but I have some objects lying around that might be RAII objects, and now I don't know where to store them or so, right? Because it's all frozen, right? If I go into suspension, all my objects keep on living. It just stops execution, but I can resume at a later point. So each of these now has their own loop, right? But it's still normal function calls on the way down, and then suspension on the way up. This still has this problem of being slightly asymmetrical, like I could also construct the stairs the other way around. So maybe there's also a way to do it symmetrically. So what if it's actually suspend, resume both ways? And this is a little bit hard to wrap your head around, but what we want to do is, so there's a caller. The caller starts invoking the first coroutine, like the source, right? Then the source runs, it produces some input. Now when the source stops executing, it suspends not back to the caller, but it suspends to the filter in the middle, right? And now the caller is on the call stack the whole time, but underneath the caller, we have first the source, and then the source is swapped out for the filter, and then the filter is swapped out for the sync, and so on, right? So I hand control directly from one coroutine to the next. And this is the last thing that I want to show you. This is called symmetric transfer. And this is a pretty interesting feature, and it's actually quite straightforward to implement. So what I want to do is, if I co-await on this transfer awaitable, I want to pass control over to another coroutine, right? Not to my caller, but to another coroutine. I'm trading places with this other coroutine. And implementing this is really simple, because we have this await suspend function from before that gets called whenever the co-await wants to put us to sleep. If the await suspend function returns a coroutine handle, then the compiler will automatically resume that coroutine in this symmetric way, right? So whichever handle I return here, I swap places with that one. So it's actually super easy to do in code, even though it's quite an advanced feature implementation-wise. So how do I do this? Well, I somehow need to know this other coroutine, right? So I need to get acquainted with the other coroutine. This is a step that I have to do somehow. I could do this, for example, during the initial construction of the coroutines. If I again have such a chain call, I could just have like they all construct once, get acquainted with the neighbors, and then go into suspension immediately. And then I just resume the top one, and then the whole chain starts running, right? But I need to make this acquaintance once, and that's an explicit thing to do. But then once I have this handle stored, what I can do in the suspend, I just say, okay, if I know somebody to suspend to, I'm going to suspend to them. If I don't know somebody, and this is something that happens, for example, during finalization, like I do not want to suspend anymore to my producer because it already finished producing all the input that it's going to give me, right? I'm now just pumping out, flushing out the final output. In this case, I'm just going to resume myself. So I'm trading places with myself, which in the end just means I don't suspend at all, right? I just continue execution. And now for the pipelines, what this means is whenever I await on such an acquire object, so the acquire object, again, the argument that I pass there, the buffer that I want to acquire the buffer from, This resurfaces in the constructor of the awaitable, normal constructor call, nothing unusual so far. So this stores the buffer internally. And now something interesting happens, because there was this await ready call from before, which determines whether we should go to sleep or not. Before we were just returning false, which means, yeah, send me to sleep, I don't care. What I can do now is, my coroutine wants to acquire a free buffer. If the ring buffer still has free buffers to give out, there's no reason for me to go to sleep, right? I can just continue running. So in the await ready, I just check, like if I still have free buffers, I don't go to sleep. I just continue, like just grab the next free buffer and continue running. Which, maybe you want to do this, maybe you don't. Maybe you look at, oh, you know, I already spent so much time in this processing step. Let's just go to the next one, right? Or decide on something else, right? So like the await ready, this gives you control over whether to suspend or not. And this is a very powerful mechanism to, like with very little code, have a huge influence on these execution patterns. And you don't need an external scheduler for this, right? You can already do quite a lot with just symmetric transfer and clever things in the await ready call. And also, remember, this is a normal object, this is a normal function call, right? So that you can have configurable, like runtime configurable behavior in there. So you can go really nuts there if you want to. Yeah, but if we do decide to go to sleep eventually, then again the trick is the await suspend, then returns the coroutine handle that we stored before in this initial acquaintance phase, and now we can pass control back around. So pipelines with symmetric transfer, like one way that I was thinking that I would like to do this, for example, is I would like to, like the I/O steps at the end, they're typically, like if it's file I/O or network I/O, they might have very high latency. So there, I maybe want to use asynchronous I/O there. I probably want to have rather big buffers there. But for the steps in between, I don't have high latency, right? Like Zlib can just run and stop running whenever it wants. So probably there I want to use like very small buffers for better responsiveness, right? So that if the user wants to cancel the compression operation, I can step right in and like stop the whole thing. Maybe I want to implement a behavior like that. The non-I/O always runs to completion and only suspends when it's input and output buffers, and for the I/O operations, if it's asynchronous I/O underneath, I can cancel it by canceling the respective async I/O call or stuff like this. Or I could decide differently, right? My point is, like if I want to do stuff like, my constraint might be I want to hide I/O latency as much as possible, right? I want to do computation while the I/O is running asynchronously in the background, and I want to do that as efficiently as possible. I can configure this way, and I hope I gave you an idea that with coroutines you can do this, and you don't even need to write a scheduler. Like you can do this by pretty small adjustments to the code, can have a big impact on the behavior. So the final result that I came up with, it actually looks pretty similar to what I showed in the beginning. I'm not going to show all of the glue code that is necessary here. If you're interested in this, you're very welcome to talk to me, and we can take a deep dive. But I hope that, like with what I've shown today, you have at least like a glimpse of like all the parts that participate in the construction of such a system, and that if you want to build something like this yourself, then you will be able to do so with the help of this talk. What I really like about this is it really decouples the concerns here, right? I can implement the processing step, I can change the scheduling logic, I can adjust buffer sizes, and all of these are very localized changes, right? So it's a very well separated architecture. I'm sure you can also achieve this without the use of coroutines, but I think, like, especially if you have all of the difficult low-level stuff out of the way, once that is done, it's actually a system that can be quite elegant and quite maintainable. So wrapping up, data processing, it's a difficult topic. It's a very common topic, but it's surprisingly challenging for such a common thing to do. Coroutines provide very powerful tools for writing such frameworks. They're by no means perfect. They're by no means the only tool to solve this, but I think they're an interesting addition to what we have available as C++ programmers. Manipulating control flow through coroutines is extremely powerful. Like, if you ever find yourself in a situation where you think, like, I don't like how the control flow is here, how control passes, like, from one component to the next, I think it's really worth thinking about coroutines, because they just give you possibilities. They change the way that you think about how execution passes from one part of the code to the next, that you typically don't have if you're only used to traditional structured programming. And I think that's probably the biggest gain that you can get from learning them, from writing some code with them. It just, like, you just start seeing execution patterns that you didn't see before. However, coroutines in C++, low-level tool, sharp edges. Not sure I would recommend using them in production right away. They would certainly need time to mature. They would certainly become a lot easier to use once we gain experience, once we get libraries. Still, if you want to get your brain mangled today, they're available on many compilers. The implementations are quite mature by now, so yeah, go nuts. Here's some references. The coroutines page on CPP reference, I actually, like, in the beginning, I found it very scary and extremely confusing, but the more I worked with them, the more valuable I thought it was, like, especially if you have this map already built in your mind. You still will need to look up stuff, because there's just so many moving parts that you can't keep all of this in your head. And then the CPP reference page can help you out. Louis Baker has an excellent blog. It's a very short blog, but it has very high quality posts. Raymond Chan did two very extensive series where he talked about lots of stuff regarding coroutines. They're a little bit hard to find because he posts almost every day, so I link them directly here. Eric Niebler, in his Rangers talk at CodeType 2017, mentioned some interesting possibilities of coroutines, which also is closely related to what is going on with the executors proposal right now. So it's aged a little bit since it was in 2017, but it's still very interesting to check out to get a feel for the vision. And in the end, the coroutines TS, it's also slightly outdated, but it's at least like one document that describes everything, like in standard ease, how it's supposed to work. So it can be a good starting point, but just keep in mind it's not the latest state. That's it. I'm happy to take questions if you have any. Thanks. Can you have multiple consumers or multiple producers? Yes, you can. It makes the symmetric transfer a little bit more challenging, right? Because, like, if you only have one neighbor for each buffer, then it is obvious who to suspend to. But yeah, you totally can. So the way that I implemented is I introduced a fork node, which basically it just holds on to its input buffer and then provides like a reference. It doesn't even need to copy provides a reference to like two different output ports, and then only once both outputs have like released their buffer back, then it goes back. Yeah, with this you have a very modular way to introduce like forks and joins in the So that works. But yeah, the scheduling becomes a bit more challenging. It's still possible, but it's more difficult and more than I wanted to cover here. Yeah, so the question is, how do coroutines in C++ compare to other languages? It's true that so I originally learned about coroutines in Lua, which has had them for a long time, and they're a lot easier to use there. They're still somewhat mind-boggling because you're not used to thinking this way, but at least you don't have like all of this boilerplate. And I mean, the coroutines in C++, they're extremely powerful, but they're very low level. So I like to compare them, like if people who do GPU programming probably know about the Vulkan API. It's a similar thing, right? It's a beast of an API. Like getting started with this, the learning curve is absolutely brutal in the beginning, but it gives you, once you're through with it, it gives you full control and you have just like immense power over what is going on. Coroutines are kind of similar. If you don't want all this power, then it's just super annoying that it's so difficult. But since as C++ programmers, we like to have full control, maybe you think it's worth it, yeah? Otherwise, if you don't think it's worth it, please wait for the libraries. Like it's, if you just want to get stuff done, they're not at this point yet. Yeah. So the question is, what will the libraries look like? Do we already know what? And I don't think we do. I don't think there's a clear consensus yet where this is going. There are some things flying around that people have been working on, but I personally think it's still too early to give an answer to that question. Other people might disagree, but that's my impression. Yeah. So the question is, since the promise is magically constructed in this storage, which most likely will turn out to be the heap, where is the awaitable actually stored? I think, and I might be wrong, but I think the awaitable, since it is constructed as a local object inside the coroutine, will be part of the coroutine frame, because the coroutine frame needs to have enough space available that it can store all of the locals whenever I may want to suspend. And I think the awaitable just lives in that same storage. So also part of this like big magical coroutine frame that the constructor somewhere constructs on the heap.